September 17, 1968, a sleek, silver train rocketed along the track between Montreal and Toronto, reaching 140.6 miles per hour. No train in Canada had ever moved that fast. The engineers called it the TurboTrain, a radical machine powered not by diesel engines or electric motors, but by aircraft turbines mounted above the passenger compartment. It promised to revolutionize rail travel, to make trains competitive with airplanes again, to prove that the future of transportation wasn't on highways or in the sky, but on steel rails at speeds no one thought possible. Except the TurboTrain barely lasted a decade in regular service. By 1982, the last units were withdrawn, scrapped, or sold off for parts. The dream died quietly without ceremony in rail yards across Ontario and Quebec. And the reason wasn't what you'd expect. It wasn't outdated technology or lack of funding or changing passenger preferences. It was something far more fundamental, an engineering decision made in the earliest design phase that would haunt every mile those trains ever travelled. This is the story of how Canada's fastest train was brought down by a flaw hidden in plain sight. The TurboTrain's origins lie in the early 1960s when American railroads were hemorrhaging passengers to automobiles and airlines. The Chesapeake and Ohio Railway, desperate for innovation, commissioned the Pullman Standard Company to develop something radical. The brief was simple: create a train that could compete with airplanes on short-haul routes. High speed, modern comfort, jet-age glamour. But the problem went deeper than just building a faster train. By 1960, American passenger rail was in crisis. Between 1945 and 1960, ridership had collapsed by nearly 80%. Highways were expanding across the continent, funded by billions in federal money. The interstate highway system was transforming how Americans traveled. Meanwhile, jet aircraft were getting faster, cheaper, more comfortable. A businessman could fly from New York to Chicago in 2 hours. The same trip by train took 16. Railroads were caught in a death spiral. Declining ridership meant less revenue meant aging equipment, deteriorating service, route cancellations. Poor service drove away more passengers. The cycle repeated year after year until passenger trains became relics, money-losing obligations that freight-focused railroads desperately wanted to abandon. The Chesapeake and Ohio Railway saw an opportunity. If they could build a train fast enough to compete with airlines on short routes, say 300 to 500 miles, they might reverse the decline. Not everywhere, not on transcontinental routes where jets dominated, but on corridors like Detroit to Cleveland or Pittsburgh to Washington, where highways were congested and airports were crowded, a high-speed train might actually work. They turned to Pullman Standard, one of America's oldest and most respected railcar manufacturers. Pullman had built sleeping cars, dining cars, observation cars for generations, but they'd never built anything like what C&O was requesting. This wasn't about incremental improvement. This was about rethinking rail travel from first principles. The project landed on the desk of Don Wetzel, a designer who'd spent years working on military aircraft. Wetzel understood aerodynamics, weight distribution, power-to-weight ratios. He looked at conventional passenger trains, heavy locomotives hauling passive coaches, and saw obsolescence. Why concentrate all the power in one massive engine at the front? Why not distribute power throughout the train the way aircraft did? Why not use lightweight materials, streamlined shapes, technologies proven in aviation? What emerged from Wetzel's drafting table was unlike anything North America had seen. The TurboTrain would be low-slung and aerodynamic, with a distinctive rounded nose that looked like it belonged on a jet fighter. The cars would be articulated, sharing trucks between vehicles instead of each car riding on its own bogies. This reduced weight, improved stability, and allowed the entire train to move as a single fluid unit through curves. But the real innovation was under the skin. Instead of traditional diesel-electric locomotives hauling passive coaches, each TurboTrain set would be self-propelled by Pratt & Whitney ST6 turbine engines, the same turbines used in helicopters. 2 power cars, one at each end of the train, would house these engines. Between them would ride 5 passenger coaches, each capable of carrying 80 travelers in aircraft-style seats. The logic seemed sound. Turbines offered an incredible power-to-weight ratio. A conventional diesel locomotive weighed over 100 tons and produced around 3,000 horsepower. The TurboTrain's power cars weighed just 45 tons each, yet together produced 4,000 horsepower. That meant spectacular acceleration, crucial for a train that would be making frequent stops on high-speed corridors. Turbines were also compact. Diesel engines, with their heavy cylinder blocks and massive crankshafts, took up enormous space. The ST6 turbines were small enough to mount above the passenger compartment, freeing up space below for baggage and mechanical systems. And turbines ran smoothly, without the vibration and noise of pistons hammering up and down thousands of times per minute. On paper, everything worked beautifully. In testing, the results were spectacular. In 1966, a prototype TurboTrain reached 170.8 miles per hour on the Pennsylvania Railroad's test track near Trenton, New Jersey. Engineers watched in amazement as the sleek train blurred past, its turbines howling, its articulated cars flowing through curves like water. This wasn't just faster than conventional trains, this was a different category of machine entirely. Canadian National Railway watched these developments with keen interest. Canada faced the same crisis as American railroads: plummeting ridership, aging equipment, routes hemorrhaging money. But Canada also had something the United States didn't: a natural corridor for high-speed rail. The Montreal-Toronto route was nearly ideal: 500 miles of mostly straight, mostly flat track through southern Ontario and Quebec. Dense population at both ends, major business centres, heavy air traffic that suggested strong demand for fast intercity travel. If the TurboTrain could cut travel time from 5 hours to under 4, it might actually lure passengers back from Air Canada. There were other advantages too. Unlike the United States, where passenger rail was fragmented across dozens of private railroads, Canada had CN, a Crown corporation, government-owned, able to make long-term investments without worrying about quarterly profits. CN could absorb short-term losses if the technology showed promise. They could commit to infrastructure upgrades, maintenance facilities, specialized training. In 1967, CN placed an order for 5 TurboTrain sets from United Aircraft Corporation, the American company that had absorbed the project from Pullman Standard. The trains would be assembled at UAC's facility in Saint-Bruno-de-Montarville, Quebec, providing Canadian jobs and technological expertise. The cost was $22 million, a staggering sum in 1967, equivalent to over $180 million today. But CN's leadership believed it was worth it. This wasn't just about saving passenger rail. This was about positioning Canada as a leader in transportation technology, about building the future. Delivery was promised for 1968 in time for a grand inaugural run that would showcase Canadian innovation and modernity. The timing was perfect. Canada would celebrate its centennial in 1967. The TurboTrain would launch the following year, a symbol of the nation's second century: modern, fast, forward-looking. The first TurboTrain arrived in Montreal in the summer of 1968, delivered by flatbed truck from the Saint-Bruno facility. Workers carefully rolled it onto the tracks at CN's maintenance complex. Its aluminum skin gleamed beneath the streamlined casing, paint still fresh in CN's black, red, and white livery. Technicians swarmed over it, checking systems, calibrating sensors, preparing for speed trials. The machine was beautiful in a stark, functional way. The nose cone swept back in a smooth curve, designed to slice through air with minimum resistance. Windows wrapped around the front of the power car, giving engineers panoramic visibility. The passenger coaches sat low between the power cars, their roofline barely higher than a passenger car, their sides smooth and unbroken except for small, rectangular windows. Everything about the design screamed velocity. Inside, the accommodations reflected aerospace influence. Seats were arranged in rows like an aircraft cabin, upholstered in bold patterns typical of late 1960s design. Overhead luggage racks ran the length of each car. Large windows offered passengers sweeping views of the countryside. The ride was supposed to be smoother than conventional trains, quieter, more refined. This wasn't just transportation, this was an experience. On September 17, 1968, with engineers aboard and data recorders running, the train was unleashed on a test track between Morrisburg and Kingston, a relatively straight section of the Montreal-Toronto main line. The morning was cool, the air crisp with early autumn, perfect conditions for a speed run. The chief engineer settled into the operator's seat in the forward power car. Around him, instruments glowed, turbine temperature gauges, speed indicators, track monitoring systems, brake pressure readouts. He checked with the crew in the trailing power car, everything nominal. He pushed the throttle forward. The acceleration was breathtaking. Unlike a diesel locomotive, which builds speed gradually as the engineer notches up through power settings, the turbines responded almost instantly. The Pratt & Whitney ST6 engines spooled up with a rising howl, not the rhythmic chug of pistons, but a sustained scream that built and built as the train surged forward. Inside the cab, the speedometer needle climbed 60, 80, 100 miles per hour. The track began to blur beneath them. Trees became streaks of green and gold. Telegraph poles snapped past in rapid succession. At 120 miles per hour, the ride remained surprisingly smooth. The articulated cars tracked through gentle curves without the swaying motion of conventional coaches. The pendular suspension tilted the passenger compartments inward, counteracting centrifugal force. At 130 miles per hour, the noise changed. The turbines reached a plateau, their scream now a steady roar. Wind rushed past the streamlined nose, creating a pressure wave that rippled along the train's length. Track joints hammered beneath the wheels. Thud, 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 marking distance at a rate faster than any Canadian train had ever achieved. At 140 miles per hour, the engineer felt the machine straining at the edge of its design envelope. Small vibrations transmitted through the floor. The steering became hypersensitive. Tiny movements of the controls translated into immediate responses. He watched the speedometer climb past 140.6 miles per hour and eased back on the throttle. They'd done it. Canada had its speed record. The train coasted down through the speed range, turbines winding down, brakes applying gently to scrub off velocity without shocking the passengers. When they finally stopped at Kingston Station, everyone aboard was grinning. The data looked good. The ride had been smooth. The turbines had performed flawlessly. This was going to work. But even during those early trials, problems emerged. Small things at first, easy to dismiss as teething troubles with any new technology. The turbines ran hot, far hotter than anyone had anticipated. The ST6 engines were designed for helicopter use, where ram air provided constant cooling at altitude. In flight, the rotors pulled fresh air through the engine continuously. On a train, especially in summer, especially when idling in stations, the turbines cooked in their own heat. Temperature gauges in the engine compartments regularly exceeded 140 degrees Fahrenheit. Engineers opened access panels and felt waves of scorching air wash over them. The metal was almost too hot to touch. Seals degraded in the heat. Lubricants broke down, turning from slick oil into sticky residue. Metal components expanded and contracted with every acceleration and deceleration, fatiguing materials that were never designed for such constant thermal stress. Maintenance crews tried everything. They added cooling ducts, installed additional ventilation fans, experimented with heat-resistant materials. Nothing solved the fundamental problem. Gas turbines designed for aircraft operation simply ran hotter than the surrounding environment could dissipate, especially when confined in the relatively small engine bays of a rail vehicle. Worse, the turbines were extraordinarily thirsty. In testing, the TurboTrain consumed fuel at 3 times the rate of a conventional diesel locomotive covering the same distance. The ST6 engines burned kerosene or jet fuel, expensive compared to diesel, and they burned it whether the train was accelerating or coasting. Gas turbines don't idle efficiently the way diesel engines do. A diesel can throttle back to a low idle, burning minimal fuel while maintaining readiness. A turbine either operates at high temperatures and high fuel consumption, or it shuts down completely. There's no middle ground. Every minute sitting in a station boarding passengers meant fuel pouring through the combustion chambers at rates approaching full power, with nothing to show for it but noise and heat. CN's accountants began running preliminary cost estimates. The numbers were troubling. Fuel consumption alone threatened to make the TurboTrain economically unviable. But CN had invested $22 million. The trains were built. The inaugural service was scheduled. They couldn't back out now. Still, CN pressed ahead. The speed record had generated enormous publicity. Newspapers ran headlines about Canada's jet-age train. Television news programs showed footage of the sleek silver machine streaking through the countryside. Politicians praised CN's vision and innovation. The public was excited. After years of declining service, finally here was something new, something modern, something worth riding. On December 12, 1968, the TurboTrain entered passenger service between Montreal and Toronto. The first runs were celebrations. CN invited dignitaries, journalists, railway enthusiasts. Champagne was served. Photographers crowded the platforms at Central Station in Montreal and Union Station in Toronto. Passengers marveled at the smooth ride, the aircraft-style seats, the panoramic windows, the sheer speed. For the first time in years, taking the train felt faster than driving. The scheduled trip time was just under 4 hours, a full hour faster than conventional service. At cruising speeds approaching 95 miles per hour on favorable sections, the landscape rolled past at a pace that made the journey feel almost surreal. Newspaper headlines proclaimed a new era in rail travel. "Canada's train of tomorrow arrives today," declared the Toronto Star. "Speed, style, mark, new TurboTrain service," announced the Montreal Gazette. Politicians posed for photographs in the modern passenger compartments, gesturing to the sleek interior, promising that this was just the beginning of a high-speed rail renaissance across Canada. The future, it seemed, had arrived right on schedule. It lasted 3 weeks. On January 5, 1969, the entire TurboTrain fleet was grounded. Multiple units had experienced serious turbine failures. One engine had shed turbine blades at speed, metal fragments tearing through ducting and damaging surrounding components. Another had caught fire in the engine bay, filling passenger cars with smoke before crew managed to shut down the affected turbine and evacuate everyone safely. A third unit lost power completely during acceleration, leaving it stranded on the main line while conventional locomotives were dispatched to tow it back to Montreal. Investigators descended on the maintenance facility in Montreal, pulling apart engines, examining burned components, photographing failed bearings and cracked casings. Engineers from United Aircraft flew up from Connecticut. Pratt and Whitney sent turbine specialists. Everyone wanted answers. How could engines that had performed flawlessly in testing fail so catastrophically in regular service? What they found was damning. The turbine installations were fundamentally unsuitable for rail service. The engines operated in an environment they were never designed for. Extended ground-level running with inadequate cooling, constant thermal cycling, exposure to track debris and dust that never reached helicopters flying thousands of feet above the ground. Every revolution put stress on components engineered for the clean, cold air of high altitudes. Bearings were failing because they couldn't dissipate heat fast enough. Compressor blades were eroding because they were ingesting microscopic grit kicked up from the roadbed. Combustion chambers were developing stress cracks because the metal was being heated and cooled, and heated again dozens of times per day, far more cycles than any helicopter engine would experience. The modifications began immediately. Engineers redesigned air intake systems, installed additional filters, improved cooling ducts. Pratt & Whitney developed uprated bearings with better heat tolerance. United Aircraft sent teams to retrofit every TurboTrain set in CN's fleet. But the problems kept multiplying, and as engineers dug deeper, they discovered something even more troubling. The turbine issues were serious, yes, but they weren't the train's only fundamental flaw. There was something else, something that had been hiding in plain sight since the earliest design phase. It was in the suspension. The TurboTrain used a pendular suspension system, a sophisticated mechanism that allowed the entire car body to tilt up to 10 degrees into curves. This was the technology that enabled those record speeds. Without it, passengers would have been thrown violently against the windows at 140 miles per hour through even gentle curves. The tilting mechanism counteracted centrifugal force, allowing the train to maintain high speeds on track geometry designed for much slower operation. The technology worked beautifully in testing. On paper, it was brilliant. French and Italian engineers were developing similar systems for their own high-speed trains. The physics were sound. The concept was proven. But in practice, under Canadian conditions, it became a maintenance nightmare. The tilting mechanism relied on hundreds of precisely machined bearings, pivot points, and hydraulic actuators positioned throughout each articulated car set. Each component had to move freely, respond instantly to curve detection sensors, and return to center with perfect accuracy. The system was mechanical poetry when it worked. But Canadian winters are brutal. Track conditions vary wildly from season to season, sometimes from mile to mile. In December, temperatures could plunge to -30 degrees Fahrenheit. Ice formed in linkages, moisture infiltrated seals and froze solid, hydraulic fluid thickened to the consistency of syrup, sluggish and unresponsive. What worked flawlessly in controlled tests on mild autumn days became a constant headache when winter arrived. Spring brought different problems. Meltwater and mud worked into bearing surfaces. Grit ground away at precision components. The pendular mechanism, designed with aircraft-level tolerances, couldn't handle the dirty, variable environment of ground-level rail operation. Sensors became unreliable, actuators stuck. The whole system required constant, meticulous maintenance to keep functioning. Maintenance crews at the Toronto and Montreal shops quickly learned to dread TurboTrain inspections. Unlike a conventional passenger car, where worn components were obvious and replacement straightforward, the pendular suspension was a complex web of interdependent systems. Diagnosing problems required specialized knowledge. A single frozen actuator could lock the entire tilting system, forcing the train to crawl around curves at conventional speeds, negating its entire advantage. And unlike a traditional coach, where a broken spring or worn shock absorber was a relatively simple fix, unbolt the old part, bolt on the new one, the TurboTrain suspension demanded complete disassembly to access internal components. What should have been a 2-hour repair job often stretched into 2 days. Entire trains sat idle in maintenance bays while mechanics traced electrical faults, rebuilt hydraulic systems, or waited for replacement parts to arrive from specialized suppliers in the United States. The cost became staggering. By 1970, just 2 years into service, CN was spending twice as much maintaining each TurboTrain as a conventional locomotive-hauled passenger set. Parts had to be sourced from United Aircraft's specialized suppliers, bearings machined to tolerances of thousandths of an inch, hydraulic seals made from exotic materials, electronic sensors that cost hundreds of dollars each. Technicians needed expensive training on systems unlike anything else in CN's fleet. The knowledge couldn't transfer. A mechanic who could rebuild a diesel locomotive was useless on a turbotrain. Every breakdown meant pulling the entire set out of service. Not just the affected car, the entire 7-car articulated set, because that's how the turbotrain was designed. You couldn't simply uncouple a problematic coach and substitute another. The cars shared trucks, shared systems, shared the pendular suspension. It was all or nothing, and the turbines kept failing. United Aircraft issued modification after modification, improved cooling ducts, uprated bearings, revised fuel systems, better filtration. CN's engineers implemented them all, sometimes working through nights to retrofit entire fleets before the morning rush. Nothing solved the fundamental problem. Gas turbines, designed for aircraft, simply couldn't handle the sustained, low-altitude, thermally punishing environment of rail service. By 1971, the turbotrains were spending more time in shops than on tracks. On any given day, at least 2 of CN's 5 sets were out of service, sometimes 3, occasionally 4. The railroad struggled to maintain even a basic schedule. Ridership, initially strong, began to fall. Passengers couldn't rely on the service. They'd arrive at the station to find their turbotrain cancelled, a conventional train substituted, adding an hour to their journey. Business travelers, the core market, switched back to airlines. The promise of 4-hour Montreal-Toronto service evaporated as mechanical problems forced slower running and frequent cancellations. CN's accountants ran the numbers. The picture was worse than anyone had imagined. The turbotrain fleet was losing money on every single run. Fuel costs alone exceeded ticket revenue on most services. Add maintenance expenses, which were running at nearly $500 per train mile, compared to $150 for conventional equipment, and the financial picture became untenable. The trains that were supposed to save passenger rail service were instead draining resources that could have been spent upgrading conventional equipment or improving track conditions. In 1973, CN made a difficult decision. Rather than pour more money into the turbo trains, they would gradually phase them out of premier Montreal-Toronto service. The sets were reassigned to shorter routes, Montreal to Quebec City, Toronto to Sarnia, where lower speeds meant less thermal stress on the turbines and fewer demands on the suspension system. It was a humiliating demotion for machines once touted as the future of high-speed rail. Even on these shorter routes, problems persisted. The turbines still overheated. The suspension still required constant attention. Fuel costs remained astronomical. By the late 1970s, the turbo trains were being relegated to commuter runs, crawling along at conventional speeds, their high-speed capabilities unused, their exotic technology reduced to expensive ballast. The irony was cruel. The turbo train's pendular suspension, the very technology that allowed it to reach those record speeds safely, was also its Achilles heel. The complexity that enabled high-speed cornering made reliable operation impossible under real-world conditions. Engineers had optimized for performance without fully considering maintainability. They'd built a machine that worked brilliantly in ideal conditions and failed miserably in everything else. But there was another layer to the failure, one that had nothing to do with turbines or suspension. It was about infrastructure. The turbo train was designed to run on existing track, the same rails that conventional freights and passenger trains used. That track wasn't built for 140 mile/hour operation. It was built for 79 miles per hour, maybe 90 on good sections with favorable geometry. Curves that were gentle enough for conventional diesel locomotives became punishing at turbo train speeds, even with the tilting mechanism compensating. Track irregularities, small dips, slight misalignments, joints settling unevenly that conventional equipment barely noticed translated into violent jolts at high speed. The faster the turbo train ran, the more it beat itself apart on infrastructure never designed to support such velocities. CN could have upgraded the track. They could have straightened curves, improved roadbed quality, installed continuous welded rail instead of bolted joints, rebuilt bridges to tighter tolerances. The French were doing exactly this for their TGV project. The Japanese had done it for the Shinkansen, but that infrastructure work would have cost hundreds of millions of dollars. Money CN didn't have and couldn't justify spending on a single experimental train type that was already proving unreliable. So the TurboTrain ran on infrastructure designed for a slower era, its capabilities perpetually constrained by century-old track geometry, its sophisticated suspension working overtime to compensate for roadbed conditions that should never have existed on a high-speed line. The final indignity came in 1982. Canadian National officially retired its last TurboTrain sets from service. Some were sold to Amtrak, which had purchased its own turbotrains in the late 1960s and suffered identical problems. Amtrak kept them running a few more years through sheer determination and constant mechanical attention, but eventually gave up and scrapped them in the mid-1980s. Other CN units were cannibalized for parts to keep the remaining sets operational. Still others were sold to museums or rail preservation groups. One complete set survives today, on static display at the Exparail Museum in Saint-Constant, Quebec. Its turbines are silent now, gutted for parts years ago. Its sleek aluminum body sits beneath a protective shed, paint fading, its once revolutionary pendular suspension frozen in place, gathering dust. Engineers who worked on the TurboTrain still speak of it with a complex mix of pride and frustration. It was an audacious machine, genuinely innovative, genuinely fast. On that September morning in 1968, when it set the Canadian speed record, it represented real achievement, proof that Canadian engineers and manufacturers could build world-class technology. But it was also a cautionary tale about the dangers of technological overreach, about designing for performance without equal attention to reliability, about solving one problem while creating a dozen others, about chasing speed records instead of building something that could run every day, year after year, without drama or headlines or constant mechanical intervention. The flaw wasn't just the turbines, though they were part of it. It wasn't just the suspension, though that compounded every problem. The real flaw was conceptual. The TurboTrain tried to bring aerospace technology to railways without fully adapting it to the railway environment. It assumed that what worked in the sky would work on the ground. It ignored the realities of Canadian weather, track conditions, maintenance infrastructure, and economic constraints. In the years after the TurboTrain's retirement, other countries developed successful high-speed trains. Japan's Shinkansen continued expanding, setting reliability records that made the TurboTrain look like an experiment in failure. France's TGV entered service in 1981, running at speeds up to 186 miles per hour, far faster than the TurboTrain ever achieved, yet maintaining punctuality rates above 95%. Germany's ICE followed in 1991, sleek and fast and, crucially, reliable. All of them learned the lesson the TurboTrain taught, even if they learned it independently. High-speed rail requires purpose-built infrastructure. It requires conventional, proven technology scaled up carefully rather than exotic systems borrowed from other industries. It requires obsessive attention to reliability over raw performance. It requires thinking not just about how fast you can go, but how consistently you can maintain that speed day after day, year after year. The Shinkansen didn't use turbines. It used electric motors, simple, robust, easy to maintain, proven in decades of railway service. The TGV didn't rely on exotic tilting suspensions. It used dedicated high-speed track, built straight enough that extreme banking wasn't necessary. When curves were unavoidable, they were designed with radii gentle enough for stable high-speed running without mechanical compensation. These trains succeeded because they embraced railway principles, not because they tried to make trains behave like aircraft. Canada never built another high-speed train. The TurboTrain poisoned the well, turning innovative rail technology into code for expensive boondoggle. When the government funded new passenger equipment in subsequent decades, they chose conservative designs, conventional diesel locomotives hauling conventional coaches, reliable, boring, slow. But they showed up on time, and they didn't catch fire, and maintenance crews could fix them with standard tools and ordinary expertise. And so the dream of Canadian high-speed rail died in those Quebec maintenance shops, killed not by lack of vision, but by an engineering flaw hidden in the very innovations that made the dream possible. The TurboTrain proved that speed alone isn't enough, that technological sophistication without practical reliability is just expensive theatre, that sometimes the most radical innovation is choosing simplicity over complexity, proven technology over exotic experiments. The lesson echoes across industries. How many other innovations have failed not because the core idea was wrong, but because the implementation ignored practical realities? How many projects have chased headlines and speed records while neglecting the unglamorous work of maintenance, reliability, and economic viability? The TurboTrain's aluminum shell still sits at Expo behind glass, a monument to ambition that exceeded capability. Visitors walk past, glance at the interpretive plaques, and move on to other exhibits. Few pause to consider what might have been if different choices had been made, if engineers had designed for maintenance as much as performance, if accountants had demanded operational viability before approving experimental technology, if everyone involved had asked not just, can we build this, but can we keep this running? The track between Montreal and Toronto still carries passenger trains today. They're pulled by conventional diesel locomotives, the same basic technology as 60 years ago. They take about 5 hours to cover the route, longer than the TurboTrain's promised 4 hours, about the same as conventional service in 1968. They arrive on time, season after season, year after year, without fanfare or excitement. They're exactly what the TurboTrain was meant to replace, and they're exactly what replaced the TurboTrain when innovation failed to deliver on its promise. What do you think? When does the pursuit of cutting-edge technology become a costly distraction from the unglamorous work of building systems that actually function? How many times do we need to learn that reliability matters more than records? And what other ambitious machines are sitting in museums today because someone forgot to ask whether brilliance in the laboratory translates to success in the real world?